Okay, we will go through the exemplar problems in the class 12 physics, chapter 4, moving charges and magnetism. Okay, before going through it, I will show you some general information. Uh, how do you find the direction of the magnetic field? So this is the current carrying conductor. Okay, current is flowing upwards, so you have to put your thumb in the direction of the current, and when you curl the finger, that is the direction of the magnetic field. Okay, here is the direction of magnetic, this is the direction of the current. Okay, now how do you find the direction of the force? Okay, when you moving charge, what is the direction of the force? So here this is the direction of the moving charge. Okay, this is v, velocity, and this is the first, this finger is the direction of the magnetic field, and this finger is point to the direction of the force. Okay, direction, this is the moving charge direction, that is velocity. This is magnetic field direction, and this finger points to the direction of the magnetic force. Okay, and then general one. Okay, when you put this cross here, that means the magnetic field is going into the plane. Okay, here magnetic field is going into the plane. Dot, it is coming out of the plane, coming out to the plane. Okay, so if we have two conductors, conductor 1, conductor 2, carrying current in the same direction, then using that thumb rule, the field is going inside here and coming out to this side. Okay, here is going inside and coming out to this side. So here now these two conductors will attract each other because of these opposite things. Here is going inside and here it is coming out. So attract each other when the current is flowing in the same direction. Okay, now if you take this conductor, one current is flowing upwards in this conductor and downwards in this conductor. Now look at the fields. Here field is going inside, it is coming out. Here is going inside and coming out. Now in between the same field is, so it will reflect repel each other. Okay, here also going inside, here also going inside, it will repel each other. Okay, the force on the conductor by the magnetic field. Okay, current conductor in a magnetic field, force explained by that conductor BAL sin theta, where theta is the angle between the current and the magnetic field. Okay, this is the Lorentz force. Okay, this is the force due to electric field and magnetic field. Okay, the combined force due to electric field and magnetic field, this force explains by this test charge. Okay, QE plus the QEB, that is cross product of velocity and magnetic field. So the E electric field, B magnetic field, velocity of the particle, F is the force on the charge, force on this charge Q. Okay, the electric field, it starts from the positive charge and ends in the negative charge. Okay, when charge is not moving, that means there is no magnetic force, because here see here this force, force due to that magnetic field depends on the velocity. Okay, if the charge is not moving, that means there is no magnetic force. When V and B are parallel, that means if you take cross product, V cross B, that is VB sin theta. So when sin theta is 0 and 180, that is parallel and anti-parallel, this will become 0. So that time also there is no magnetic force, that is theta is 0 or 180. Okay, magnetic field lines starts from the north pole and ends in south pole. Magnetic field lines. Inside the magnet, the field lines goes from the south to north. Okay, outside it from north to south. So that means field lines are inside the, they are forming the closed loop, going inside the magnet also, outside the magnet also. This is Biot law. This is the electric field due to the element. So this is the formula. You can refer to the book also. Okay. When there is a cable, current carrying cable like this, and its radius is a, that is cross section is a. If you are measuring the magnetic field within that circle where R1 is less than that R or A cross section, this is the formula. Where R it is the radius of the cylinder, that is A cross section of this cable, and R is the distance from the center of the cable. Okay, that is the circle radius of that circle, and I is the current carried in. Now if you take some point outside this cable, so what is the magnetic field? And that is mu I by 2 pi R2. R2 is from the center, the distance to that point. Okay, from the axis of the cylinder. So here R is much greater than the A, that is radius of that cable, cylindrical cable. So magnetic field at the center of a solenoid. Solenoid is a number of coils. So we will see it in the book. So mu naught n I. I is the current. N is the turns per unit length. Okay. N is the total capital and total number of turns. Per unit length is the small n. Okay. The length of the solenoid. Magnetic field. Within the turns of this is toroid. For toroid, this no magnetic when charge is not moving. I already told you. Magnetic field at the center of the arc. If you have a arc, what is the magnetic field? So you can use this formula. For the circular coil B at the center. Okay, this is the one. The number of turns in the coil, radius of the coil. So this is when an electron is revolving in the orbit, and this is the magnetic field. So here the number of rotations, okay, charge of the electron and radius of the orbit. Okay, two charged particles travels identical electrical path in a completely opposite sense. Okay, and the uniform magnetic field in this direction. Then this is they are asking which select one. Okay, so this is one, the charge to mass ratio, that is the specific charge. Okay, because they are oppositely charged, when adding two E by M ratios will be 0. Okay, that is specific, is called specific charge. Okay, here this is a helical path, and the formula here you will see, you use this formula, so you will find that specific charge, two oppositely charged things will be 0. Biot law indicates that the moving electrons with velocity v produce magnetic field such that V and B are perpendicular. Okay, 12. So here you see direction, the magnetic field direction is perpendicular to the plane carrying this, that is current V. Okay. A current carrying circular loop of radius r is placed in the xy plane with the center of the origin. Now half of the loop with x is greater than 0 is now bent so that the new so that now it lies in the yz plane. Okay. So first we have to compute the magnetic moment with the one loop, then for the two loops, that is two of the loops. The first magnetic moment is in the z direction because it is the xy plane perpendicular to that magnetic moment, that will be z direction. So now if you split into two things, then one will be in the z direction, other will be, this will be in the x direction, that magnetic moment, the other will be in the z direction. Okay. Question number 3. Now we are computing the magnetic moment. Okay. Magnetic moment, the combined magnetic for the one loop. This is the IA, area of the loop is the I into current into area of loop is the magnetic moment. This is for the single loop. We get this. This is the magnetic moment in the z direction because that is in the xy plane. Now we split into two loops. One is on the xy, other is yz. Xy, the magnetic moment will be in the z direction. Here the area will become off because only half the loop. So this will be in the x direction. Now if you combine that magnetic moment, so this is the magnetic that is less than this. Okay. So that means now the magnetic moment diminishes. Okay. 27. So here is the formula for the magnetic moment, current into area. An electron is projected with the uniform velocity along the axis of the current carrying the long solenoid. Which of the following is true? The velocity is electron is projected uniform velocity along the axis of the current carrying solenoid. Solenoid, the magnetic field will be on the axis of the solenoid itself. Now the electron is projected also along the axis of the solenoid, so they both are parallel to the magnetic field. So the force will be QV sin theta, so that will be 0. The angle between V and B now is 0, so that means force will be 0. So it will not have any effect on the moving electron. There is no force because it is projected with uniformly along the axis of the current carrying solenoid, because solenoid's magnetic field also in the axis of the solenoid. The electron will continue move with uniform velocity along the axis of the solenoid. See here, this is C between V and B. Now there 0 means that means force will be 0. In cyclotron, the charged particle undergoes acceleration all the time. So you can go through how the cyclotron works. This is the cyclotron formula. Here you can go through how this work when you change the what is this? All the time the acceleration changes. Okay, here whenever the charged particle moves, or Here polarity of these two disks is keep on changing, so acceleration will be keep on changing. A circular current loop of magnetic moment m in the arbitrary orientation, the external magnetic field B work done to rotate the by 30 degree about the axis perpendicular pole is there will be no change in the loop, okay, because when you rotate work done will be magnetic moment and b cos theta, cos the angle between the magnetic field and the magnetic moment. So it won't change, this angle won't change after rotation, because here saying current carrying when in the rotation, see the work done to rotate on the axis perpendicular to the plane, okay, the magnetic moment is also perpendicular to the plane and this is also perpendicular plane, so the angle won't change when you rotate along that axis, so there is no work is required, so zero work will be done, okay, because here cos cos theta, okay, it won't change, the angle between this m and b won't change even after the rotation. The gyromagnetic ratio of the electron in an HA atom according to the Bohr's model. Okay, here is the formula. Magnetic moment of the electron divided by the angular momentum of the electron, and this is the formula, magnetic moment divided by the angular moment. After that you will get this charge by the magnetic moment. Independent of the orbit, because that is not depend on the n, so it's negative because charge is electron is negative. Consider a wire carrying a steady current I placed in a uniform magnetic field perpendicular to its length. Consider the charge inside the wire. It is known that magnetic force do no work, because work done is FD cos theta angle. The angle between the force and V is 90 degree, so the cos 90 is 1. Magnetic force no work, okay. Distance covered, the angle between the force and the velocity is 90, that means is cos 90 is 0, so it won't do any work. Some charges inside the wire, there is surface V, okay, and the wire moves under the influence of no work it is done, okay, because of this formula. Two identical current carrying coaxial loops carry current I in an opposite sense, okay. A simple ampere rule passes through this, okay, because here the current going in the opposite sense and the ampere loop covers both the currents, the total current will be 0, because the current enclosed is 0 because they are opposite sense, so this side will be 0, so here no term will come, so this is wrong. Value of the independent of the C, because the total current is 0, then independent of that loop. There may be a point and C where B and D, okay, this for B depends on the surroundings only, okay. B depends on not only the current but also the surrounding, okay. This B not only depends on the enclosed current but also the surrounding, so it need not be 0. A cubical region of space is filled with some uniform electric and magnetic field. The electron enters in, okay. Positron has the same mass as electron, but it is positively charged. Okay, you have to use the Lorentz equation for this, and you will these three answers. Magnetic force on both particles cause the equal acceleration. Both particles we have the same mass, but it is positively charged. The particle, okay. The charged particle would continue to move with a constant velocity in the region. Okay, so here when electric field is zero, so the charged particle the velocity won't change, but the direction may change. Okay, B and V are perpendicular, it may move, but direction may change, but velocity won't change. It is a constant velocity. Here we can balance E and B. Okay, so for the constant velocity, charge particle would move the constant velocity in a region where, so is it possible that you adjust electric field and magnetic field like in velocity selector, so that it will move with the constant velocity. Here E electric field not zero means it can affect the velocity, so this is not the answer. Here and 0 there is no net force, so it can travel with the constant velocity. So these three are the answers. Okay, question number 12. Verify that the cyclone proton frequency has the correct dimensions of this time. 12. Okay, if you go through the cyclotron, this is the formula. Magnetic force and is equal to the centrifugal force. You see, then after simplification, this will become velocity by distance. Okay, so here velocity is length per time. Okay, so LT minus 1 divided by L, so this is the T minus 1. R is the radius of the circle, W is the angular frequency. Okay, so that the force does no work must be a velocity dependent force. Okay, you can go through this answer. So here d is the distance, that means velocity into time, so force into distance. Okay, so you can go through it velocity dependent. The magnetic force depends on the V, which depends on the inertial frame of reference. Does then the magnetic force differ from the inertial frame of frame to frame? It is reasonable that the net acceleration is different from the so 37 114. The magnetic force is frame dependent. Net acceleration arising from this, however, frame independent. Non-relative physical, and okay, you can go through what it is. Okay, the velocity dependent force Here you can go through what is this inertial phenomenon. Describe the motion of a charged particle in a cyclotron of frequency, radio frequency. If the frequency of the radio frequency field is doubled. So see, this radio frequency changes the polarity of these two disks. Okay. So here you can go through how the cyclotron works. The particle will accelerate, this deaccelerates because they are changing polarity of the disk. So the radius of the paths in the disk will remain unchanged. Two long wires carrying current arranged, okay. One carrying on the x-axis, okay, this direction, and other carrying current in this direction, okay. Now the current is flowing in the opposite, this direction one and this direction. The other current is okay. Now what is the verse 16? Okay, this is now they are asking what is the force here? Force here due to this current. Force here due to this current is I2L. B1 is the magnetic field due to this current, because magnetic field here due to I1. Okay. Now B1, the direction of the B1 and I2 are in the same direction if you use that thumb rule, okay. So you can find out this direction. So because this is the same direction, the angle between these two is 0, okay. Then force here at this point is 0 due to this. Two parallel elements. A current carrying loops consists of three identical quarter circles, okay. 1/4 radius of lying in the positive x, y, z. The planes of the centers origin join together. Find the direction and magnitude of the B. 17. So it has the three components of the magnetic field. So you can see the net book for the details. A charged particle E of mass m is traveling in an electric field E in the magnetic field. Construct the dimensional quantity. Same I showed you for the question number 12 also. And electron enters the velocity in the, that is I x direction. Electron in the x direction, cubical region parallel to the coordinate plate in which there are uniform magnetic field. The orbit of the electron is bound to the you have to use the Lorentz equation 4.19. Okay, this is the answer. Two magnetic forces obey Newton's third law. Verify that two elements located at origin and this. So here Y position is at R. There is a Y position, other it at origin 0 0, both carrying the same current. So you have to find the magnetic field and the force formulas. Order 20. If you use that, then force due to dA2 on dA1 is 0. For this and this is non-zero. And a multi-stage voltmeter is constructed using the galvanometer as shown this. We want to construct the voltmeter that can measure 2 volt 20 volt using the galvanometer resistance. Galvanometer resistance 10 ohm. It produces the deflection at this is amperes. Okay, here is the circuit. So now the current plus is equal to 2 for the 2 volts up to this resistance. When you include this resistance and the current, you will should get 20 volts for 20 volt range. These two resistance are included, and you include all the resistance, you get 200 volts. Okay, there are three equations and three unknowns, and you will get these values. Galvanometer resistance is 10 ohm. A long straight wire carrying current rests on the table as shown here. Another wire PQ of length 1 meter mass carries same current but in the opposite direction. Okay, I already showed you when they are going in the opposite direction, when current going in the opposite direction, then it will repel each other. Okay, this will repel this, this will repel this. The wire PQ is free slide abnormal, so to what height that PQ will rise? So when currents are going in the opposite direction, the magnetic field will repel each other. I will show you. So that repelling force you have to equate to the gravitational force. Okay, because the gravitation pulling down, the repelling force is moving it up. 22. This is the force. That force you have to equal to the mg, gravitational force. Then after that you will find what is the height. Okay. Underturned rectangular coil ABCD explained is hung from the arm of a balance. A mass here they have mentioned mass, not weight. Okay, it's a mass. Gram is added to the other end to balance is a current is passes through the oil. Constant magnetic field of this Tesla. So they are asking how much additional mass must be added after passing current. It is pulling it down. This is pulling it down, so we have to add some weight. Asking to find that weight. 23. Initially, if you don't pass the current, then torque is 0. So they are adding 500 gram on the other side to balance it. So now the weight of the coil they were finding. So when you pass the current, the magnetic field is pulling it down. The torque is active. So that is you have to add this additional this weight. Okay, mgl. So now we have to, this additional weight is equal to this force. That is the extra force which is pulling it down. So now after solving this, we have to add the 1 gram. This is extra force. So here this is the torque. Okay, so you can go through this how this formula is arrived. Here area, then magnetic field, current, everything is coming in this formula. A rectangular conducting loop consists of the two wires in the opposite end. These wires are each of the wires in material with the cross sections, so they are differing the cross sections. Okay, the equal wire has a resistance of R, the low resistance, which in turn is okay. Now we have to find the torque. 24. This is the one. So this is the force. This current here by R, and using that cross section. More cross section means then the less resistance. Okay, resistance will be less. Resistance is inversely proportional to the cross section. So you are finding this force. Now because this angle is 45 degree they are given, 1 by root 2. B is 45 degree. Okay, so 24. An electron and positron released at from these coordinates respectively uniform magnetic field. The original momentum magnetic field, under what conditions the direction of the momentum will orbit in the non-intersecting cube. 25. So you can go through these answers. Okay, both define the circle of radius, or they shall define circle in the opposite sense. So you can go through this. A uniform conducting wire of 12A, this is the length. Resistance R is wound up carrying the coil in the shape of equilateral triangle, square, the regular hexagon. The coil is connected to the voltage. You find the magnetic moment. Okay, here total length is 12A, so that we have to split. This is 4 sides, that means this will 12 means, so each side will be 3, and here 3 sides, so each will 4. Here we have 1 to 6, so each will be 2. The area, magnetic moment is the current in the area. Okay, and the number of sides also they given. 4 sides, 3 sides. Here what is this? So here this is the answer. Okay, consider the current, circular current carrying loop of radius R, then consider the integral. Okay, 27. So you can go through the answers in this. Okay, you can go through the details here. A multi-range current meter can be constructed by using a galvanometer as shown here. We want current measure. Okay, this is resistance. Find this S means shunt resistance. Okay, so resistance to construct a meter of like this, measure this. 20. So here at first this is parallel with this thing for the 10 milliamps. Okay, all the three resistance are parallel with the all the three shunt resistance. For 10 milliamps, these 1, 2, 3 are parallel with these two points, and these 2 points they are parallel. Okay, for the 100 milliamps, so these two parallel with the galvanometer and this one. Okay, this one parallel, and for the 1 amp this one. Okay, when you solve this you will get this is actually ohms. Okay, this is in ohms, this is in ohms actually. S1 S2. 5 long wires carrying current and arranged in the edge of the pentagon as shown in figure. Each current is out of the paper, so it's a dot, they are coming out of the paper. What will be okay? So 29. This is for the symmetrical, this is 0, and for this second condition, third condition. What will the magnetic intention at point O? Because due to symmetry, that is 0. What will the field? If one of the wire A is switched off, the current is here is switched off. So that when it is 0, this current is on. When it is switched off, these currents, effect of this current is opposite to this. Okay.